Okay, thank you everyone for, I guess, sticking around for the last talk. I'm very excited to be here and tell you about, very briefly, unfortunately, about recent work on quantum annihilers, obviously, but something that's, I guess, a little bit remote from what I've been doing recently. This is joint work with Peter Young and Tamim Albash, both of whom are here. And this is basically a different way to use quantum annihilers, I would say, as we're used to, or compared to what we used to. So here's the, I guess, the premise and the setup of the study. So we know, I mean, usually when I'm here, I actually have kind of bad news. I keep telling you that quantum annihilers are maybe not very good for optimization, but I thought maybe today I'd take a different route and tell you about, I guess, another way of looking at or finding a quantum advantage using quantum annihilers, which is to use them not as optimizers, but as substitutes for quantum Monte Carlo algorithms. So the idea here is to basically use the usual scenario of quantum annealing and interpolate between a driver Hamiltonian and a problem Hamiltonian, but we anneal not all the way to the end to solve an optimization problem, but we stop somewhere in the middle at some value of the annealing parameter, S star here, and sorry. Okay. Never mind. So the idea is to basically anneal all the way to a certain point and then perform measurements of the quantum Hamiltonian in some basis, the Z basis or the X basis. And basically by doing that, we can collect, by repeating this annealing and stopping in the middle, we can collect statistics and calculate the thermal averages of different properties of this quantum system at basically zero temperature, ideally zero temperature. Now, the fact that we anneal all the way to some target S value means that, of course, quantum annihilers will be slow because we need to slow down when we approach the minimum gap, for example. And also we have to repeat this in order to get good statistics for whichever quantum Hamiltonian quantum system that we want to study. Physically, we have to repeat, oh, thanks. Good. We have to repeat the process over and over again until we get good statistics. Now, if we look at classical methods that do the same thing, that obviously classical optimization algorithms that many of us have been working on will not do, because it's no longer a classical system, it's a quantum system. So if we want to study the physical properties of quantum systems, what we normally do is use quantum Monte Carlo. But as you know very well, I guess, quantum Monte Carlo does not always work. And this is because for some systems we have the infamous sign problem. And it appears when we have, I guess, non-stochastic fluctuations in the Hamiltonian. And actually, I was very pleased to learn that D-Wave already have this on, I guess, either on plans, or actually you probably have something like that that's already working on, at least on a small scale, which is wonderful. And so this is about that in some sense. And because quantum Monte Carlo is expected to kind of converge really excruciatingly slowly on these sign problematic systems. And in order to check that, or to show that, we have been looking at a very specific model. And this is it. It's a Hamiltonian that has a transverse field on one hand, and it has a sigma z problem Hamiltonian, but it's defined. This is just a problem set that we thought about, studying. So we know that it's actually a random antiferromagnet defined on a 3 regular graph. We know that it's a hard problem to solve. It's a max-cut problem. But we also added basically in the middle sigma x terms, where the sign in front of the sigma x is positive, which means that the system is non-stochastic. The fluctuations are non-stochastic. So if we think about how quantum annealers will do on these systems, then quantum annealers will be impeded by the gap or the minimum gap as we approach the target S value or the point where we want to stop and take measurements, whereas when we look at quantum Monte Carlo, then quantum Monte Carlo thermalizes slower around these minimum gaps, as I guess many of us know, but it also has the sign problem now. These are two separate issues that quantum Monte Carlo has to overcome. And to see whether this is so, we studied random instances of these random antiferromagnets on 3 regular graphs. We generated many instances with different sizes. And we wanted to see how quantum annealers will do. So how quantum annealers do? Well, we have to calculate basically this term here, which is the derivative of the Hamiltonian with respect to the annealing parameter sandwich between the instantaneous ground state and the first excited state divided by the gap squared. And the maximum of this guy there is basically an estimate of the quantum annealing runtime. We also want to see, or we need to check how many times we have to run the quantum annealer to get the statistics that we want. If we want, for example, the error bars to be, the relative error to be small, then we need to basically count the number of times we have to repeat the annealing process, and this, of course, factors into the overall runtime. And to do that, we used exact diagonalization. So the systems that we studied were up to 24 spins. Now, in the quantum Monte Carlo setting, we just measured the number of sweeps that we need to, I guess, perform until we get the same error bars. So here are some results. So first, for this term there, which is, again, the derivative of h with respect to s sandwiched between the 0 state and the 1 state divided by the gap squared. If anybody knows of a name for this term, let me know. I'd be happy to use I guess a short name for this guy who is important for us here. Anyway, this quantity there, we calculated it for different values of, I guess, the annealing parameter S, and for the different instances, basically the figures on the right show how this quantity behaves as a function of S. In 3 cases, the one that I told you so far about was the non-stochastic XX term present, but we also looked at what happens if we flip the sign of the XX, and we also looked at what happens if we remove it completely. What we find is that, I guess, if you look at S values between 0 and 0.4, for example, and you look at how this thing behaves, then you see that for the stochastic, these 2 guys are stochastic in nature, and the value of this term is somehow contained. Look at the vertical scale, goes all the way to 10 to the 1 maybe, but when you look at the non-stochastic values of this term, they really jump up. So the quantum annealing runtimes for non-stochastic Hamiltonians are longer, basically, but it's not a point of this presentation because I want to focus on the non-stochastic case. I'll just kind of wanted to mention it as like a side remark. Anyway, if we then look at the typical value for different problem sizes of this guy, we basically can estimate the quantum annealing runtimes as I guess, as a function of problem size. And it depends, of course, on when we want to stop, because we want to measure the maximum of the typical maximum of this guy up to the point where we want to make the measurement, to perform the measurement, because anything that goes beyond that is irrelevant. So this is how the scaling with respect to problem size of the quantum annealing runtimes for different values of stopping point, S star equals 0.3, 0.4, and 0.5, and we get different scalings. I guess, for example, the 0.4 for the non-stochastic case looks, I guess, the most legitimate one, but we can focus on that if we wish. But we get a scaling of the quantum annealing runtime. Now, for the number of measurements that we need to take, it's interesting. I won't go into that because I don't think I have too much time. But it turns out that you can calculate, if you want to get a relative error that is pretty much constant, then you can look at, to estimate the number of annealing repetitions you need to do, you can look at actually the variance of the physical property that you want to actually count, and it's nice because you can do that. And when you look at, these are different basically physical properties and the number of measurements that you need as a function of problem size, and you see that they actually go down, which is interesting. I will not go into why, but it's actually physical. The systems are bigger, and so we have a kind of self-averaging of the average value of whatever it is that we want to measure. Now, going to how quantum Monte Carlo is doing, what we find is that the sign problem turns out to be very severe. We were actually having problems even I guess getting good statistics for 6-spin systems with some like beta of 4, for example. So the sign problem, which again, I don't know if we want to go into that, but if we want to calculate a sign problematic Hamiltonian with quantum Monte Carlo, we have to actually thermalize the stochastic version of that Hamiltonian. So it's the wrong distribution that we're thermalizing, but we can correct by adding a very oscillatory function, which is actually the sign of the weight, and into the denominator. So if we want to calculate the thermal average of something, then we look at we have to divide two quantities, and the one below is called the average sign, and it's basically a very oscillating function depending on the sign of the weight, and these are really going from positive to negative very rapidly. And so the average sign, which as you can see it, for small value of the sign basically tells you that the error bars on this guy are huge, and the sign actually for a 6-spin system can go to something times 10 to the minus 4, which is really small, which means that we need to take very many measurements, even for such a small system for which exact diagonalization is very simple. And if we want to understand how the quantum Monte Carlo runtimes scale with inverse temperature, we find that they scale exponentially with beta. It may come as no surprise to some of you, I don't know. They also scale exponentially with system size, and this is because the average sign goes down exponentially with both system size and beta, which means that the quantum Monte Carlo runtime actually scales exponentially with those two, with the product of those two parameters, inverse temperature and problem size. And interestingly enough, we also find that it actually, the severity of the sign problem changes very dramatically depending on what the target S value is, where we stop. And actually the sign problem turns out to be, the average sign or the severity of the sign problem turns out to correlate with the minimum gap, with the gap of the system, which to me is very interesting. And this is also something to think about, I guess. So the point is that the number of measurements that you need even to solve small problems is really huge. It could be very huge. So the thing is that I would have liked to show you scaling, basically scaling with size of quantum Monte Carlo and scaling with size of quantum annealers, but I can't. And the reason I can't, while I have scaling with size for quantum annealers, I don't know what the scaling, or we don't know what the scaling with size for quantum Monte Carlo, because we just can't basically get enough measurements even after months of running them on clusters. We can only, I guess, use extrapolation methods using, you saw, I guess, the kind of the poor quantum Monte Carlo result. You see just 3 points, 12, n equals 12, 14, and 16 for very moderate beta values. And just this means that it's really hard. It's so hard that I can't even show you results, basically. But we know, again, that quantum Monte Carlo runtimes, they scale exponentially with beta. They scale exponentially with n. Now, if we want to calculate the ground state properties of a physical system, what should the beta be? And the answer is that the beta should be greater than the gap. Now, if the quantum Monte Carlo runtime is scaled exponentially with beta, and beta is the gap, it means that, for example, if we want to stop at the minimum gap, then the quantum Monte Carlo runtime will scale exponentially with the minimum gap. But we already know how quantum annealing runtimes scale with the minimum gap, just basically inversely proportional, or maybe 1 over gap squared. And so the point is that I really don't have a figure to show you, but I hope I convince you that there's something there that's interesting, because we can kind of show or demonstrate that quantum Monte Carlo does really bad or scales unfavorably with the gap, whereas quantum annealing runtimes, as we know, scale only polynomially with those. I'll just summarize. So the preliminary results, I guess, show that quantum Monte Carlo is really slower than quantum annealing for sign problematic Hamiltonians. The form of the scaling advantage depends on that gap. So if we have a polynomially closing gap, then we could get easily an exponential speed up. But again, so far we have only extrapolation results, because we just can't get the averages right. It just takes too long. And so what about interesting applications? So for starters, obviously you can do simulations of quantum systems, because this is exactly what I showed. But there was an interesting paper recently by Brenda et al. That showed that there is, or I guess you can connect to solving semi-definite programming problems using this, so you can actually solve classical problems with quantum Hamiltonians in some sense. I will just, I guess, end with saying that it turns out that non-stochastic terms are really hard to build experimentally, even though D-Wave were successful in doing so, which I'm really pleased to hear, because I think this is a really good way forward. And I didn't talk about, what other classical methods you could do other than quantum Monte Carlo, and some people mentioned that maybe tensor networks or machine learning algorithms, but these are approximation methods, and we could still study them. They certainly don't feel the sign problem in the traditional sense, but I think things are in some sense looking up, and yeah, this is, hopefully we'll write it up really soon and put it on the archive. So that's it. Thank you very much. Thank you.
Questions?
So the work of Professor Nishimori seems to indicate that non-stochastic interactions might only be useful for avoiding first-order phase transitions in annealing, when we get to higher order Z interactions in the physical Hamiltonian. Presumably you can simulate that in your quantum Monte Carlo system for an interesting problem. My guess is that the quantum Monte Carlo might actually not be as disadvantaged in that case because the physics of the non-stochastic actually softens the gap. Can you speculate on that?
So it's true. I mean, the Nishimori result basically tells you that adding non-stochastic terms indeed can bring you from a first-order phase transition to a second-order phase transition. But you could, if we can build it on a quantum annealer, then we could do it. But doing it on with quantum Monte Carlo or classically, we can't do it. So quantum Monte Carlo with non-stochastic terms, I don't see how you could do it efficiently. So I think that the result by Nishimori basically tells you that while you can do something interesting on a real quantum annealer, doing non-stochastic, it doesn't mean, or actually it means that you can't, with the tools that we have today, do it with quantum Monte Carlo. So I hope I answered your question if I understood it.